Cool. G'day there, Level 3 Physics. We're just going to start throwing some new concepts and ideas at you while you're working on your experimental physics. We're going to start learning about mechanics. And so there's a new idea that I want to throw at you guys today. And that's this idea of centre of mass. And so centre of mass is not an idea that we had back in year 12, but it is something that if you're a PE student, you're kind of familiar with centre of mass, centre of gravity. They're the same thing. And for your physical body, it's like you think about a line going down the middle of you and a line going through the middle of you, and your centre of mass is kind of that central point through which all forces on you appear to act. And so in physics this year we can actually calculate centre of mass, and we're kind of thinking, zooming out on the universe a bit, thinking on an astronomical kind of a scale, thinking about point masses like planets or whatever, different distances apart. We can actually calculate the centre of mass, because x centre of mass, distance to the centre of mass, is m1x1, mass 1 times distance 1, plus m2 x2 plus m3 x3 m4 x4, you can keep going, divided by m total, kind of averaging the mass out of that to find the average distance. That gives us the distance to the centre of mass. And interestingly, where those distances are measured from, where all those x's begin from, is completely up to you. You can choose where those x's are in order to make your problem solving experience a little bit easier. We might have a go at one of these. Okay, so here's a little one for you guys to have a go at. Example, you got a dude, 80 kilograms, going for a walk in isolation with his dog, their dog. Dog's mass, 20 kilograms, length of the lead out to the dog, 2 meters. How far is it from the dude to the centre of mass of the dog and the dude? That's what I want you to work out. Pause the video, have a crack. First step. Did you spot doing that? That's what we've got to do to make this easy for us. If we make our measurements start from the centre of mass of the dude, make that distance 0, then it's really, really easy for us to solve this problem. 80 times 0 is just 0, 2 times 20, 40, 40 over 100, 0.4. .4 meters. Let's make some physical sense of that. What we mean is that from the dude .4 meters away is the centre of mass. And that's kind of what we expect. We expect it to be closer, much closer to the dude than to the dog, because the dude's got more mass than the dog, and so we expect that there'll be a bigger influence by the dude on the centre of mass than there is by the dog. Okay, so here's another example to really see if you get what's going on. What we've got is the Earth, mass 5.98 times 10 to the power of 24 kilograms. It's really big. And the moon over here, only 7 times 10 to the 22 kilograms. The distance from the Earth out to the moon, that's 384,400 kilometres. Pause the video, find that centre of mass. The first thing I'm going to do is choose my arbitrary point as the centre of the Earth. So all those distances are going to be measured from the centre of the Earth. Times by 0, so who cares? don't forget to convert kilometres to metres. So, you plugged all those numbers into your calculator, right? Hopefully you ended up with 444,7603 metres. Convert it to kilometres so it makes sense. 4448-ish kilometres. About 4,000 kilometres from the centre of the Earth to the centre of the Earth-Moon system. What does that mean? Well, it turns out that the radius of the Earth is 6,400-ish kilometres. So the radius of the Earth is bigger than the distance from the centre of the Earth to the centre of mass of the Earth-Moon system. So where is that centre of mass? It's actually underneath Earth's surface. About 2/3 of the way from the centre to the surface is the location of that centre of mass. And so you might be sitting at home thinking, but why do we even care? Let's have a little think about why we might care about centre of mass of an object. And so one aspect that we really do care about is when we're applying a force to an object, when you're pushing something. And so if you push something, the dot here represents the centre of mass. And if we apply a force, if we push something through its centre of mass, we cause linear motion, we cause it to move in a straight line. But if we apply our force not through the centre of mass, off the centre of mass, then we're going to cause linear motion, we're going to make that move, and we're going to make it rotate, we're going to make it tumble, as well as moving. Try it with an object at home. Try it with something on your kitchen table. Give it a push through its centre of mass and it will move. Give it a push outside of its centre of mass and you'll make it move and make it rotate.